All right, so now let's talk about something called direct evaluation. So direct evaluation can happen whenever a function is continuous at a certain value. If you're and so a good example is polynomial functions, and that's what this one here is. So if you have p of a, which is a polynomial function, or p of x is a polynomial function, I should say, and you have the limit as x approaches a, well, first of all, we know that polynomial functions are always continuous, right? They're going to be, they're going to have some type, peaks and valleys and things like that, like a quadratic, a parabola, that's a polynomial function, right? A linear function can be considered polynomial. But with polynomial functions, they're always going to be continuous, right? And so if I say, if I have some value a that I'm approaching, so let's say that a is right here on the number on the x-axis, right? Then if it's continuous, then whatever it approaches from the left is going to be the same as whatever approaches from the right is also going to be the same as whatever this output is, which is f of a, right? It's going to be the exact same as whatever that value is. And so when you have a continuous function, all you really have to do is put that input, or put that value that you're approaching in as the input into that function, and that'll give you the limit, right? Because if it's continuous, you don't pick up your pencil from the page, right? It's gonna be going through that point, and either way, it's gonna be approaching that point from the left or the right. Okay, and so if you take a look at checkpoint 2.12, that's what this is saying, right? So if I just take if I have this polynomial function here, this is continuous everywhere, right? The domain is negative infinity to infinity. There's not a point in the domain that doesn't exist, right? Because there's not any kind of limitation. If I cube a number, I can cube any number, and I get a real number. I can multiply numbers by 2 and I get a real number. I can multiply by 3 and I get a real number, right? Like there's nothing here that would restrict or eliminate any elements in our domain. So this is a continuous function. So I could use our limit laws like we did before, which may be more, sorry about that, which may be more efficient than using a table or something like that. But even more efficient, all I need to do is just plug in -2 to these values and just really, or as the input, and just evaluate this. Okay. All right. And so I can just plug this in my calculator, or I can do some mental math or work it out on paper, but make sure you use order of operations one way or the other. And so we'll end up with here -24 plus 4 plus 7. And so that'll end up being -13 as far as I can tell. All right, so here's a look at the graph on Desmos just to kind of solidify this. So we have this same function, right? 3x cubed minus 2x plus 7. And so if I approach, here's where 2 is, right? Or -2, I should say. If we approach -2 from the right, we're going to get closer and closer to -13 here. If we approach from the left, we're going to get closer and closer to -13, right? And that's also the same as our output at that particular point, right? When we plug in -2, we get out -13, right? So this is f of -2, right? I also did it here just so you can see that f of -2 is -13. So if it's a continuous function, all you have to do is plug in that value, and whatever the output is at that point is also what the function approaches, right? If it's continuous. And so that's another shortcut that might make life even easier than using the laws. Okay, so there's a validation for that. Now, the same thing is true for rational functions. If you have a rational function where you have two polynomial functions on top and bottom, then you can just input the value that you're approaching into each of those functions as long as the denominator doesn't equal 0. Okay, if the denominator equals 0, like we saw with the quotient law, then that brings up a whole different scenario. Okay, and so if I'm looking at this one here, all I have to do is plug in 3 as the input, right? And then just evaluate it, just do some PEMDAS. As long as it exists, right? And I can just easily check in the denominator. If I plug in 3, 5 times 3 plus 4 is not going to be 0, right? So that means that this is true. That's not the case. And so we can directly evaluate this, all right? So I'm going to say, okay, this is going to be 2 times 3 squared minus 3 times 3 plus 1 all over 5 times 3 plus 4. So I'm just putting 3 in as my input into all those x locations, right? So now we can do some order of operations. So it's going to be 3 squared is 9, times 2 is 18, negative 3 times 3 is negative 9, plus 1. And on the bottom we have 15 plus 4. So this will come out 2. 18 minus 9 is 9, plus 1 is 10. 15 plus 4 is 19. That cannot be reduced, and so that'll be our final answer. All right, and just to check to see if this works graphically, we can see that if we have that same function here, right, this is what the function looks like. And this function isn't continuous everywhere, right? There is an asymptote that we can see right here, right? But it is continuous at 3, right? We can see at 3 right here, we can approach from the left, or excuse me, from the right, we can approach from the left, and we end up at that same point, which is f of 3, right? And it ends up being 0.526 approximately, but exactly it ends up being, if you plug in 3, find f of 3, it's 10/19. Okay? All right, so direct evaluation can work if you have functions that are continuous, right? And so it works with polynomial and rational, but it actually works with any function as long as that function is continuous at that particular point. Okay. All right. So bring any questions you have to class, and we'll definitely get a chance to practice these and get help, and you'll get a chance to just work with your classmates and hopefully support each other and get this even, hopefully understand it even better than you do at this point.